we start with separation of variables. What is separation of variables? Well, it's when you have a differential equation in the form dy dx as a function of two variables, x and y, and you can rewrite this as dy dx is equal to the function of x times another function of y. So we separate the two variables. And then in order to solve this type of problem, we put all the y's on one side and the x's on the other side, and then we integrate on both sides and solve these two calculus problems. So we integrate this with respect to y, and we integrate this with respect to x, and then ultimately, if possible, we solve for y. Now, what we're going to do is study non-separable differential equations. So in a non-separable first order linear differential equation, we'll have something in the standard form dy dt plus p of t y is equal to g of t. This can also be written in a symmetric form with different variables as dy dx plus p of xy is equal to g of x. So sometimes we see differential equations with t as the independent variable, and sometimes with x. We're probably more familiar integrating with respect to x, but time ends up very often being the independent variable in differential equations problems. How do we solve this? Well, we'll set up an integrating factor, mu equals e to the integral of p of t dt. And then we need to integrate this problem. This is called the integrating factor, and our solution here will be y of t equals 1 over mu times the integral of mu times g dt, and then all in parentheses plus c. Okay? Here we'll have mu, or the integrating factor, is equal to e to the integral p of x dx. So this is the integrating factor. Notice it's the same as this integrating factor, but with x. And then we'll have y is equal to 1 over mu, open parentheses, integral mu g dx plus c. So we can get the solution in either form, in either variable. The only difference being here we integrate with respect to t, integrate with respect to t, here integrate with x, here integrate with x. Okay, let's do an example. Our first example is y prime minus ty is equal to 0. In this case, we can write this as dy dt is equal to ty, noting that t is the independent variable. And then we can separate the variables by putting all the y's onto one side and all the t's onto the other. So dy over y equals t dt. And then we can integrate on both sides and solve. So when we integrate the left-hand side, we'll have the natural log of the absolute value of y plus c1 is equal to, on the right-hand side, t squared over 2 plus another constant. These two constants can be combined. So this is the natural log of y is equal to t squared over 2 plus c3, where this c3 can be thought of as c2 minus c1. Then, how do we solve for y? Well, we can use the inverse property of exponential and logarithm. So here we can raise e to this exponent and e to this exponent. E and ln are inverse functions, and so this cancels and becomes y, while on the right-hand side we have e to the t squared over 2 plus c3. Here, this is e to the t squared over 2 times e to the c3, and this whole term is itself just a constant. And so we can rewrite this now in the final form of the general solution as y of t equals c e to the t squared over 2, where this constant c is equal to e to the c3. So this is our general solution to this differential equation. We can, of course, also just quickly verify that this is in fact the correct solution. So in order to do that, we should first compute our y prime here. So note in this case that we would have y prime equals, this is going to be c times 2t over 2 e to the t squared over 2. These 2's cancel. So we end up with y prime minus ty will look like y prime, which is c t e to the t squared over 2, minus t times y, which is c e to the t squared over 2. And notice that this term is the same as this term. This is ct, this is tc, so that indeed satisfies this differential equation. So we have verified that is the correct solution. So that would be solving the problem by separation of variables. Now let's try solving the problem by integrating factor method. So looking at the problem, instead of using separation of variables, let's try using the integrating factor method to do the same problem. If we write this as y prime plus minus t times y equals 0, then comparing that with the integrating factor method, we'll find that we have a minus t term that looks like p of t, and a right-hand side function, g of t, that equals 0. So this is now in the form y prime plus p of t y is equal to g of t. What does the integrating factor method say to do to solve a problem like this? The integrating factor method says take mu equals e to the integral of p of t dt. So let's do that. Integrating factor method says our integrating factor mu is e to the integral of p of t dt, which is e to the integral of minus t dt. What is the integral of minus t dt? It's e to the minus t squared over 2 plus c. Now, this was not stated explicitly in the method before, but in our integrating factor method, we're always going to just make this 0. Make 0, okay? The reason for that is not immediately obvious. It comes from the derivation. This will simplify your life tremendously to do this. So whenever you're computing your integrating factor, just make the constant of integration 0. You don't have to, but you should, and it will make your life easier. Now we find that y of t equals 1 over mu of t times, open parentheses, the integral of mu of t, g of t, dt, plus a constant. This c is just a constant. Then we want to substitute in our mu and our g. So this will become equal to 1 over mu, which is e to the minus t squared over 2, times, open parenthesis, the integral, mu e to the minus t squared over 2, times g. What's g? G of t is equal to 0 dt plus c. 0 times this exponential function is just 0, and 1 over e to the minus t squared over 2 brings the exponent to the numerator. So this simplifies to e to the t squared over 2 times the integral of 0 dt plus c. The integral of 0 is 0, and this constant remains. So we have this is e to the t squared over 2 times 0 plus c. Then this is just c e to the t squared over 2. So you could think this is 0t plus another constant plus c. Either way, this is just going to be plus a constant. So ce to the t squared over 2. So now what we find is that y of t is equal to c e to the t squared over 2. And you'll notice that this is the same answer that we got before. So indeed, the integrating factor method seems to produce the right answer. So although This is not a proof. This at least gives us hope that this method should work.